Hello, hi everyone. Welcome to PyData Global. We're very excited to have you here. Um, I am it's my absolute pleasure to introduce John Nordby. He will be talking about microcontrollers and machine learning using MicroPython. Uh, John is a machine learning engineer specialized in IoT systems, and he is also the co-founder and head of data science at Sound Sensing. Let's give a warm virtual welcome to John. Thank you.
Hello, thank you so much for the warm introduction. Let me put up the slides here. And Python is very familiar to everyone here, but the fact that you can run Python on small devices, such as a smartwatch type device or a kind of a security camera type device or audio sensor, that might not be familiar to everyone, or portable devices like this. So that's what we'll talk about today. First, I'm co-founder and head of data science Sound Sensing. We use sound vibration to analyze machinery such as heating, cooling, and ventilation systems, which is used by many customers across Norway. And we use Python for basically all of our stack, backend, of course, data science, of course, machine learning, etc. And we also do use it for prototyping of sensors, which is relevant for today's talk. So the goal of this presentation is that you, as a Python developer, can build an IoT sensor on a microcontroller using MicroPython, so that you don't need to learn any new language. You will use your existing skills and then add a little bit new knowledge about MicroPython. And it will also include more advanced functionality, such as running on-edge machine learning using a library called emlearn MicroPython, which I have developed. So let's jump straight into it. First, what is a microcontroller? So microcontrollers can be extremely small and low-cost devices, but also these days you can get a rather powerful machine, complete with Wi-Fi connectivity, Bluetooth connectivity, USB, etc., for just a few dollars. So this chip, which is ESP32S3, it costs $2.5 for just a chip, and you can get a board for just $6, and has 32-bit CPU running at over 200 megahertz, floating point unit, several megabytes of RAM and flash, which compared to, say, 10 years ago, it's a lot of resources on such a low-cost device. So that means we can actually run a relatively full-featured environment, not a desktop environment, but a programming environment. And these days, you don't have to tinker a lot with the hardware itself unless you're very interested. You can get ready-made devices, also very affordable, which also then includes some sensors, for example, accelerometers for motion, or microphone for audio data, camera for video data, etc. So this is become very accessible in the last years. And MicroPython is a small independent implementation of Python 3, which is designed for these devices, and it even runs on even smaller microcontrollers. And you can install it by downloading a ready-made binary to flash onto your device. And on ESP32, you use this command line tool called ESP tool to flash the device. Just two simple steps, and then you have when the device is rebooted, it takes maybe 30 seconds, then you have a prompt of Python running on your device. So if you're connected over USB, you can start interacting with the Python that is then running on that little device. There's also some nice tools, one tool called MP Remote, which is for kind of running on your machine so that you can easily interact, for example, copy files back and forth, or easy access to the REPL, or just one command to run a script on the device, etc. You can also use an IDE, of course, and we will show Viper IDE a bit here today. And as a first example, we'll just discuss how one would make a temperature sensor. So in this example, using the device on the left, which has an accelerometer, and that also has a built-in temperature sensor. So we will just read that. That's not the greatest temperature sensor because, for example, if the device is charging, it might get a little bit hot around the battery, which is close to the sensor. So you might want to have, for a proper solution, you might want to use an external temperature device. Maybe you want to put it into water if you're tracking, I don't know, brewery, or maybe you would like to have a device for room monitoring. Then you can buy device shown on the right, which also has then humidity and CO2, and you can also get particle sensors and many other kind of devices. But the approach from the programming point of view and will be exactly the same. So you can use Viper IDE. It's a zero install tool because it runs completely in the browser. And so when you use Chrome, you can connect to a device directly over USB. So in, for example, in an educational setting, if you're a teacher and you would install MicroPython on the devices, you could just give the students a MicroPython device, and they could use Viper IDE, and they don't have to install any tools on their machine. It also works on Android tablets, I believe. So that's a really good getting started experience. And then, of course, you can use the command line with MP remote if you want. Just show this as an easy way to get started. So the code for such a sensor, we can use a library, so called MQTT-AS. That allows to send data over MQTT, which is a very standard IoT protocol. Has some nice benefits over HTTP, including good support for binary data, and also it's a broker architecture, which is easier to manage. So we will just have a main loop, and we'll actually use async IO. So async IO is supported on MicroPython, and very convenient for sensor devices because you're often doing several things at the same time. Here we just have one simple task, the main task, which first connects, and this does both the Wi-Fi connection and then the connection to a MQTT broker, so somewhere to send the data. And then in the loop, we will read the temperature from the accelerometer in this MPU.temperature. That's a property which actually will ask over I2C, ask for the temperature from that little sensor. And then we will publish this over MQTT to a topic. That's how MQTT works, and we just send the temperature data as a string. Then we sleep until it's time for the next temperature. And that's the entire process. So this shows the simplest case of a practical sensor with MicroPython. So this is stuff that if you program any Python before, you will be quite familiar with all the things. The things that are a bit new are, of course, some of the libraries. And then the library called machine, that's where what comes with MicroPython in order to access kind of hardware type features. Yeah, so if we would try to run this in Viper IDE as it is, we would get a problem. We would get an exception on this first line because the MQTT-AS is not included in all versions of MicroPython. Same with this MPU 6088. That's external libraries. So MicroPython has a package manager, which we can use to install such third-party packages. And Viper IDE also supports this. For the common packages, there's a nice list, but this is a custom third-party package. So we can use this install package via link and paste in the link to GitHub repository with a little bit of metadata in that repository, and it will automatically install the library. And then here we would also do that for the MQTT-AS, and then we will have a running system. And you can also do this on the command line, of course, with MP remote. Or if you have a connected device that is on Wi-Fi, you can actually do it completely on the device as well. So this is a very powerful feature and not really standard in a small embedded device, but it really brings that familiar Python experience where if you're missing something, you Google and you find something that will help you install it, and you're off to the races. It's fantastic. So that's a simple temperature sensor. But can we go more advanced? I mean, Python is not known to be the fastest programming language, and these devices are quite constrained on RAM, CPU, etc., certainly compared to your mobile phone or your laptop. But we can actually use MicroPython for a range of use cases. Basically, everything that is feasible given the type of hardware we can do with MicroPython, because we have C modules, and I'll explain a bit about those later. So we can do temperature logging, etc. We could also do accelerometer tracking, that you may be dealing with 100 hertz data rate, 100 measurements per second. If you do sound, it's easily 16,000 samples per second. That needs to be managed, otherwise you will not process it in time. And the same with images. So I wouldn't call this video processing. We can do, for example, say 1 to 5 frames per second at a low resolution, but enough to make useful or fun things. Like you could have a thing that opens the door only if it's your cat that is showing in the camera. And this is possible via C modules. So an example, which is in the EMLearn repository, it's a sound sensor, and to follow the conventional way of measuring it, there's a few steps that you need to do. You can try to do it in pure Python, and I tried, and it was just a little bit too slow. Here you can install this example from this repository. If you have, this is designed for this T camera. If you would have a different device with a different microphone, you would need to make, of course, some changes to the pins, like where is the microphone connected. But there's a one-click install, which is also a super nice feature of Viper ID. You can make these examples, and you can have a one-click. You click there, and then you get put into Viper IDE. You connect to your device, and it will install all the libraries the dependencies that are needed, and also the files that are specific to the example, along with if you have, for example, any data files. So there is an example of that, which is a rather more data intensive tool, where we're processing the audio and then computing the sound levels in the standard way that is used in noise regulations, etc. And there's also an example there of showing that on the screen, so that what's going on, as well as sending it to Blink to get a dashboard. And yeah, there's also a small UI toolkit by Peter Hinch, which is used in examples. So what we do in the C code, there's a weighting filter, which uses infinite impulse response filter. It's a common type of filter, and that's the most difficult part, and that's implemented in C. This is not the code for that particular module, but a simple C module that illustrates how we extend MicroPython in C. So one can write some C code. In top, there's a factorial helper function which does the calculation. There's another function which takes MicroPython objects in and out. This is C code, but they represent the Python objects. And then this can be registered to a module. And then this is basically a binding, so that this will be then accessible in MicroPython and callable as a Python function. And this can be implemented in a library like EMLearn does for a lot of DSP and machine learning functionality. Or, of course, most of the modules that you interact with from core MicroPython, they are implemented in this way. So many examples that you can look at. But a super cool feature in MicroPython is that these modules can also be installed in using the package manager. So you can install new native modules at runtime. And this is unique for embedded systems. I haven't seen this feature in any other system. And to make this possible, it needs to be what's called a native module. And you can just copy such a file onto the device, and there's some metadata and so on that makes it possible. Of course, you need to have the right, it needs to be a matching architecture. Viper ID understands this, so it can actually automatically pick the right version and architecture for you. There are a few limitations that are being worked on, but I hope that in the future this will be kind of the standard way of doing C modules in MicroPython, because it's both powerful and super convenient. Just as convenient as a Python script. There's also something called external C module, which is included in the firmware build. So it's a little bit less flexible, but it's a mechanism that's been there for several years, and it also that will allow for code sharing between C modules, so it can be a little bit more efficient, especially in terms of space. But I hope that there will be more and more these native modules going forward. Okay, so that's what's a little bit about sound and how we can use C modules to process data, and DSP, digital signal processing sample of sound. Here's an example of machine learning. So this is an example of an activity tracker. This is become kind of standard functionality on a smartwatch or fitness watch, and common might be to just detect like the overall category. We will, and that's nice, but you probably already have such a device that can do it. You can probably do it on your phone. And it could be nicer to do something custom. So here I have just an example that a friend said, it would be cool to track how much I'm exercising, or to make sure that I do enough repetitions, for example, of each of the exercises. So I collected a small data set. This is also an example which is in the emlearn MicroPython repository. So I can collect this small data set using this device, which has this built-in accelerometer, also has built-in battery, so it just runs on its own. And you can click the button to indicate which activity you're going to do. Because for machine learning, we need this label data set first, with markings of what is what. And then afterwards, we will learn a classifier that can, on new data, can determine what it is. But first, we need these labels. So you can label directly with this device, and it will record into 10-second long NumPaper files. And I did like 3 separate series with around 1 minute activity per activity. And I did 4 activities, where other is like just walking around the house, doing maybe some household chores, etc. Because it's important to be able to separate that from any of the others, so we don't get a lot of false positives. And then afterward, the data is collected. I can transfer it over USB, because there's with MP Remote, you can just copy files. You can also do it in Viper ID, copy files from the device to your computer. And then I clean the labels using Label Studio. So here's some examples, and you can see, for example, jumping jacks is very clear. It's very quite high energy activity. So you see each of these represents like 1 repetition. The lunges are less energetic. The squat, you can see in the middle plot here, you can see how clearly the motion going down and up, down and up. So each of these series is the 3 axes of the accelerometer. So it can detect how much you're accelerating in the different directions. And then, it could be hard to make to program with some rules like how to separate these. That could be quite tricky. So that's what machine learning is useful for. Because then we can pass the data to a learning algorithm. And the way that this is done for this kind of task is that you split the input stream of data, the accelerometer data, into windows like time chunks. And in this case, I selected 4-second chunks because each repetition can take up to 4 seconds, so you need to capture all that. And then you pre-process into some features, pass it to a classifier model, and then that will spit out what's going on, or what the model actually at least thought was going on. So features, there are many ways of doing this kind of extraction. With some simple statistical features can actually do quite well on this kind of task, as long as we're looking to detect the rough classes, like we have 4 classes and they have quite clear, rather big differences, at least when we look at them over 4-second period. And then we just write Python, or write a MicroPython compatible code for processing this. And we use this both in the training pipeline, which runs on my machine, my laptop, and then also will run on the device. So we are sure that this is actually compatible. This is critical in this kind of machine learning. And then it's nice that you have this, you can run the code with Python both on your laptop and on the device. It makes this much more feasible to make sure that it's 100% the same calculations. Otherwise, your model will just mess up. And we use NumPy files for this. So I made a tool for writing NumPy files in MicroPython. Just linked below. So when you have you decided on the extractor, you can run a pipeline. This is also in the example, so it's kind of standard here. And this trains the model, and this just takes, I think, under 20 seconds. And it's using standard scikit-learn. So if you've done any machine learning before, you'll be very familiar with this process. The thing that is a bit, it comes in addition, is that we use the emlearn library in order to convert this model, which is a scikit-learn model, into a CSV file, which is the kind of the decision rules for this random forest classifier, in a way that can be read by emlearn MicroPython on the device. So when you have that file, you just copy it to the device. It's also nice. You can do a kind of a live update or remote update of the model, and it's very easy to then load this model on the device, because emlearn MicroPython has this implementation around the forest that you can just load this CSV file into. So it's just a few lines to create the model and load the decision boundaries, and you get. And this is then implemented in C. And this there are some tools that generate Python code for such a classifier, but this C-based approach with MicroPython bindings is 10 times faster and also 10 times more space efficient. So this shows the benefit again of using C modules for these kind of things. Here it would be acceptable to use just pure Python. If you would have more computationally intense process, like higher sample rate, then it might actually, you might be completely necessary to do this with C. So to summarize, we saw that I tried to illustrate that the modern microcontroller devices are very accessible. You can run Python, which is already fantastic. It's a language that you probably know, and if you are learning it, now you know that you can also use it for embedded devices in addition to data science and everything else. I recommend starting with an ESP32 type device. They're very good, cheap, and powerful, and popular, so there's a lot of help. Viper ID is a great way of starting to develop, and MicroPython is a productive environment for sensor devices. It has a familiarity and ease of use of Python, has the MIP package manager, which is really good, and also has good support for connectivity, such as the Wi-Fi, Bluetooth, etc. It's easy to send the data, and also USB communication. And you can implement advanced processing, so it's not a toy at all. It's a serious tool that it's not very limited, especially because we can use these C modules to extend. So you can process accelerometer, audio, image, radar, any kind of sensors that you can connect to these devices. You can feasibly process with MicroPython, at least if you use some C modules occasionally. And then emlearn MicroPython is a set of C modules that implement DSP and machine learning functionality. And I didn't cover that many. We covered the infinite impulse response filters and this random forest decision trees. But there's also FFT, fast Fourier transform, also a convolutional neural network for image classification in the library, and k-nearest neighbors, which you can use to implement on-device learning. So you don't have to go to a laptop to learn, but you can learn directly on device. And also some shout out to other tools that are useful in space. ULab is a NumPy implementation for MicroPython, quite full-featured, very powerful. And OpenMV is a kind of implementation of OpenCV, a computer vision and machine vision library for MicroPython. And I've also done a couple of other presentations that have a little bit more information about this topic. So that's all I had. I hope this gave you a inspiration and some information on how you can get started with microcontrollers, use MicroPython, and also going all the way to machine learning tasks.
Perfect. We have a couple questions that I will now show on the screen.
Yes.
So the first one is, have you tried compiling the entire Python app with Numba? Just curious if I could use the Numba compilation instead of C directly.
This would be a very advanced exercise. So Numba compiles native code and has kind of knowledge of C, etc. However, it is quite tightly tied to C Python. So as far as I know, there is nothing that will kind of emit C code which is not tied to C Python, so the desktop Python. But that would be, of course, extremely interested. But as far as I know, right now, there is no practical way of doing this. But I will mention one more thing there, sorry. There are actually Numba-like decorators in MicroPython, which allows to accelerate some MicroPython code. And the presentation I did for South Africa has some of that, and there's also a few information, or a few recordings from PyCon AU, which goes into depth about those decorators and how they can help.
Okay, brilliant. The second question, I think your last slide may have also covered some of that, but just in case you have anything to add.
Yep. Yes, so yeah, there's no full NumPy, but there is, ULab is a good option. I just use array.array because that's a standard type. That's a one-dimensional thing, which means that you also need to keep track of, for example, if it's 2D, you need to keep track of how many items do I have per row. You just pass that around. So that's to make it not custom at all. So it's just a standard data type.
All right, brilliant. If there are no further questions, then thank you everyone for joining us today. And if you want to continue the discussion, we do have a PyData Global Discord. The link should be available in your welcome emails and in the AirMeet links area. Recording of the session will also be available shortly afterwards for anyone who wants to rewatch this. Thank you again, and we'll see you at further talks. Bye.
Bye. Thank you.